We started this lecture series in 1992. This is the 16th time that we've run this lecture series. And I did a little calculation to find out how many people might have been sitting in seats like yours over that period of time. And we quickly understood from our figures that it's over 100,000 people. We've run this lecture series in Fairbanks and in Anchorage and in Juneau. And one year we ran it also in Seward. So it has had a lot of exposure, but it's also had a lot of listeners and a lot of viewers like yourself. So this is what you're part of, something that is a big trend in Alaska to want to learn about science. And we're glad at the Geophysical Institute and the University of Alaska to be providing that opportunity. And tonight we are very fortunate to have Travis Rector to come and talk to us. You know, there are not many people that when you enter a name into Google, it comes up as top of the list. And that's what happens with Travis. I just tried this out this evening. You enter Travis Rector into Google, and the top item in the list is his website with pictures of items from the heavens, many of the pictures of astronomical items of interest. So you should go look at that. But he's a person who is notable. And he's a member of the International Astronomical Union. You might know that recently there was a meeting of the International Astronomical Union concerned about Pluto. And he's going to tell you something about that, I think. I won't tell you which side he was on the argument. I'll let you hear that from him. But his background, he got a PhD in astrophysics from the University of Colorado in 1998. And since then, he has worked at Kitt Peak Observatory, which is in the western part of the United States in Arizona, and also at the National Radio Astronomy Observatory, which is in New Mexico. And that was for 3 years in the first place and 2 in the second. And in 2003, he came to the University of Alaska Anchorage and joined the Department of Physics and Astronomy. Well, maybe it's not. Is it the Department of Physics and Astronomy? Okay, I got it right. Thank you. That was a guess. And he has been a lecturer there since then as an assistant professor. And he tells me he's up for tenure this year, so we were all rooting for him. And so at this point, I want to introduce him as the speaker on this topic. The topic I have isn't quite what it says on the slide there, and I think it's a little more interesting the way it says, as you read it on your poster. It says he's going to talk to us on what constitutes a planet, the debate over Pluto. Travis Rector, please welcome him.
Hi, everyone. Thank you for the introduction, and thank you all for coming out. It's nice to be back in Fairbanks again, though I have to say I'm a little bit disappointed because living in Anchorage, we imagine that it's 40 below in Fairbanks every day of the year. And so when I checked the weather yesterday, and it actually was pretty darn close to 40 below, I thought, oh, well, I'll finally get to experience that, and I come up here, and it was actually warmer in Anchorage. It was warmer here than it was in Anchorage. So a little disappointed about that, but that's okay. So again, my name is Travis Rector, and I'm a professor at the University of Alaska Anchorage, and I'm an astronomer in the Physics and Astronomy department there. And as you mentioned, I'm also a member of the International Astronomical Union, which is the organization that voted on Pluto in August of 2006. And so I want to thank the Science for Alaska people for inviting me up here to talk to you about what we did in 2006. So some of you may have a different perspective on what we did, and so I'm going to talk about the different perspectives. So this is my alternate slide for the talk that I'm giving. So in 2006, in August, members of the International Astronomical Union, including myself, met in Prague of the Czech Republic, and we met for what's called the General Assembly of the IAU. And this is sort of the sort of the Olympics of astronomy. We meet every 3 years for 2 weeks, and a whole range of different subjects are discussed. And I have to say, I don't study Pluto, I don't study planets, I study black holes and active galaxies. So I was at the IU to present research on that, but all of the members of the IU were there also to discuss various issues, including how we should classify Pluto. So I'm going to take a few minutes here and show you some pictures from the General Assembly. What these are pictures of the last day of the meeting. And over the 2 weeks, several different things, including the issue about Pluto, were discussed, and several measures were proposed. And at the last day of the meeting, we voted on those measures. So this is just a picture of the auditorium where we all met and to discuss it. So the woman up here is a famous astronomer named Jocelyn Bell Burnell. She's famous for discovering pulsars, and she's the one who led the discussion on what we should or should not do with Pluto. This is a picture of a colleague of mine sitting next to me. I covered his identity to protect the innocent or the guilty. And what he's holding up is the yellow card that we use to vote. And there's several different issues that we voted on, most of which are not of interest to people. And then after we voted on those, we moved on to the issue of discussing what is it that makes a planet. And so that's what I'm going to talk about to you today. Now, there's a bunch of text up here that I'm going to go over in greater detail, so don't feel like you have to read and understand that all right here. But basically what we did is we voted on 3 things. The first thing we voted on was how will you define a planet? And this is just a listing of the criteria that we use to define a planet. And I should mention this is the first time that the IAU had actually bothered to try to define what a planet was. Prior to this, it was pretty obvious. If you see a planet, you know what it is. And then the second, and in that vote was the vote where we just differentiated between what's called a planet and what's called a dwarf planet. And the next issue that we voted on was whether or not dwarf planets should also be called planets. And from an etymological perspective, this is about as dumb as it gets. But that's what we had to vote on. And so you can see up here, Jocelyn, she had a balloon, which was to represent the gas giant planets like Jupiter and Saturn. And then she also had Pluto, and then she had a box full of cookies, or biscuits, as she's called it, since she's from England. And then she had an umbrella over there over all of them to say whether or not they should all be considered planets. And that issue was voted down, so technically dwarf planets are not considered planets. And I won't say why that's a good or bad decision quite yet. And the final thing that we voted on was whether or not objects like Pluto, whether or not they should be classified as something called Plutonian objects. And this was something that was voted down. So we discussed the 3 issues, and astronomers were invited to participate. So here's a slide just showing one astronomer coming down to a microphone to discuss the issue. And then finally, once everyone had a chance to speak, we all voted. So this is the famous photo of all the astronomers voting on whether or not Pluto should be reclassified as a dwarf planet. And as you can see, the vote was overwhelmingly in favor of it. Those holding up a yellow card were the ones in favor of it. And so over 80% of the people there, including myself, voted to reclassify Pluto as a dwarf planet. And so as of this moment, Pluto was no longer considered of the planet class. Now, after we had that vote, we all cackled maniacally, and we went out and had a drink and stole candy from children and kicked puppies, and it was really a lot of fun. It's a shame you couldn't have been there. Now, needless to say, not everyone was thrilled about the decision we made, and so a quick search of the internet found out a lot of the displeasure people had. Riots immediately broke out in the streets. People were smashing cars, turning over vehicles, and the riot police had to be called in. Okay, well, that didn't exactly happen, but there was actually a protest that was staged peacefully at New Mexico State University in Las Cruces. And there were some people had a sense of humor about it, so here's some banners that people put up. This is one of my favorites. Start calling Pluto an asteroid and it'll start acting like one. We never actually voted to call it an asteroid, but I can understand the sentiment. And another thing that was really cool is that the word Plutoed became actually chosen as the new word of the year for 2006. To be Plutoed meant you were demoted. Whether or not it was with cause or without cause is still debated, but This was voted the word of the year. And this is my favorite. Of course, anything you do will be put on the internet and someone will try to make money off it, so you could buy bumper stickers and t-shirts. And this is my particular favorite because it says, Pluto, never forget. Well, that's not a picture of Pluto, that's Jupiter. So whoever made this already forgot what Pluto looked like, so I'm not sure what they're forgetting or not forgetting. And this is kind of sad, but the whole event was actually foreshadowed by an event that occurred in 2004, where the Pluto character at Disney World was actually run over and killed by a float. So if anyone asks you who killed Pluto, the astronomers were not the first to do it. And for those of you who are watching Good with Grammar, you'll notice that Pluto was killed after being run over and killed. He was killed twice in this awful incident. Something we shouldn't laugh about, but we do anyway. Okay, so that's what happened. And so I want to talk to you a little bit about who is the IAU and who are these awful scoundrels that made this terrible decision, and what gives them the right to do that anyway. God darn it. So first off, the International Astronomical Union is a professional organization, and these are astronomers who do research. And what the organization does is it decides mostly matters of protocol. And so to be a member of the IAU, these are the criteria that you have to have. So you have to have established yourself as a research scientist. And then the next question is, well, what do they do? Well, there's a bunch of different things that the IAU does. And the thing that affects most people actually has to do with the naming of celestial objects. And then we also handle things dealing with nomenclature, and that's how the whole Pluto issue came up. So the way you'll interact with the IAU mostly has to do with the naming of objects. And so if you've ever seen something like this, one of these services where you can buy a star name or something like that, these services are mostly fraudulent from the standpoint that only the IAU gets to decide what the name of an object is. And the reason why we do that is to prevent every object from having thousands of different names. So when I discover a galaxy, I can't just go say, oh, that's Travis's galaxy, or I'm going to name it after my wife or my dog or something like that. What we do is when we discover a new object, we submit the information about it to the IAU, and then they handle the naming of the object. And so that way, when we describe an object, everyone in astronomy knows what we're talking about. So if you want to go buy a star, you can do that, and you can pay your $50, but all that happens is they just put your name of your star in a book, and that's all that it is. And if you want to pay me $50 and I'll put your name in a book, I'm more than happy to do it. Now, fortunately, most of these services do actually acknowledge that what they're doing is not authentic, and this website was proud to see actually acknowledge that only the IAU is allowed to do this. So if you want to do this, this is fine. I mean, they'll make you a plaque or they'll put you in a book, but the important thing is that unless the IAU gives it its official name, professional astronomers won't recognize it as such. So that's what we do. Now, one of the things I think is interesting about all this is I've talked with many people who have been very upset about it, and first of all, I'd like to apologize for that. It was not our intent to upset people. But I was talking with a friend, and he was just so angry about it, and I knew that if we weren't good friends, he would have been a lot more choice in his words with me about it. But finally I had to say, well, why do you care so much? I mean, just tell me one thing about Pluto. What do you know about Pluto? And he just said, well, it's out there. That's what I know. It's small and it's out there, you know, and that's what makes Pluto special to us. So what I thought I'd do is talk a little bit about what Pluto is and some of the misconceptions people have about it. So just a few things to mention of it is that, first of all, did you know that Pluto is named after the god of the underworld? This is the Roman name for the Greek god of Hades, which in modern culture would also be the devil. So if the planet Pluto were named after the devil, I'm not sure people would be quite so upset that we demoted it. Now, the reason why I got this name is when Pluto was discovered, an English schoolgirl proposed a name because since Pluto is so far away, they figured that's the realm of darkness, and so it would be an appropriate name. Now, Pluto is very far away. It's about 3 billion miles away, and 3 billion, unless you're looking at a McDonald's sign or the national debt, is not the kind of number that you normally see. So I thought I'd take a second to explain how far away that actually is. Now, sometimes astronomers like to use measurements in relative terms of how far light can travel in a certain amount of time. So for example, a light year is how far light will travel in 1 year. Now, light is so fast that it can go around the Earth's equator about 7.5 times in 1 second. So that's how fast light travels. That's also about how long it takes light to travel from the Earth to the Moon. So it's about 1 light second. And for those of you who remember the transmissions from the Apollo astronauts, there was about a 1 second delay from when Houston would contact the astronauts on the Moon, and then another second from when it came back. Now, Pluto is a good deal even further away than that. The Moon is 1 light second away. The Sun is about 8 light minutes away, which means if the Sun were to turn off right now, we wouldn't know about it for another 8 minutes. Of course, up here in Fairbanks, we wouldn't know about it for a couple more months. But that's how long it takes light to get here. Now, Pluto is so far away that it takes light 5 hours to travel from the Sun out to Pluto. So think about that. The Moon is 1 light second away. The Sun is 8 light minutes away, and Pluto is 5 light hours away. So if you think about how long 1 second is, that's easy to imagine. 8 minutes, that's also easy to imagine. For those of you who are fans of classic rock, that's almost exactly how long Zeppelin's Stairway to Heaven is. And if you think about 5 hours, how long that is. So Pluto is really, really far away. It's really far out there. And since Pluto is so far away from the Sun, it's in a region of space that's very cold. And so Pluto is pretty much a giant ice chunk. And in reality, it's really not that much different than the ice that's stuck to your rear fender right now. It's so cold there that it's 400 degrees below 0 Fahrenheit. So if you've complained about the temperatures around here lately, just be thankful you're not on Pluto. Now, another thing that's interesting to note about Pluto, as far as trying to classify what kind of object it is, since Pluto is a giant chunk of ice, if you were to bring it closer to the Sun, say like the distance that the Earth is from the Sun, bring it from 5 light hours into 8 light minutes, it would actually turn into a comet. It would start to melt, and all the gas as it melted would form into a tail blowing away from the Sun. And so the only difference between Pluto and a comet is that Pluto is just fortunately far away enough from the Sun that it doesn't start melting. So that brings us to the first piece of things I want to bring up, and that is the names that we choose for objects is often situational. It doesn't have to do with what the object intrinsically is, but it may have to do with where it is, and that's another issue that will come up. Now, you've probably heard that Pluto was discovered by an American astronomer, a fellow named Clyde Tombaugh, and he discovered it using one of the telescopes at Lowell Observatory in Flagstaff, Arizona, and he did it in 1918. Now, the reason why Clyde was looking for planets was because prior to this, there had been successful attempts to discover planets using a technique called gravity perturbation, which basically is when you watch the planets move through the sky, you can see how the planets speed up and slow down as they pass by other planets. And originally, people only knew about the planets out to Saturn, but by watching the motions of Saturn, people were able to figure out that there was other planets beyond it, and then eventually Uranus was discovered, and in a major accomplishment in astrophysics, another planet beyond Uranus was predicted, and it was predicted to be in a specific location, and they went and found it. And so that was when Neptune was discovered. So people were really excited about looking for planets because 2 planets had been successfully found by watching the orbits of the planets. And based upon measurements of Uranus, they thought that there may still be another planet out there, which was called Planet X. Now, Percival Lowell, who is a very wealthy man from Boston, was the guy who built Lowell Observatory. See, you build it, you get to name it. And he was hiring people to look for Pluto, look for this Planet X, and Clyde Tombaugh was the guy who found this planet. And at first they thought it was Planet X, and so that's how it got classified. Now this picture here, these 2 pictures show Pluto, and you can see it's the little dot there on the left, and you can see the arrow pointed at it, and the dot moved over to the right. And so what they do is use a technique called blinking, where they go back and forth between the images, and they could find that. So Tombaugh found the image, found Pluto, and initially they estimated Pluto's size to be about the size of the Earth. Now that's, as I'll talk about in a minute here, is a lot smaller than the other planets in the outer solar system, but they thought it was a lot bigger than it is now. And so after some debate, they decided that it should be labeled as a planet. Now here's a picture of Pluto taken by the Hubble Space Telescope, and these pictures are really not very good, and the reason why is because Pluto is incredibly small, and as I mentioned before, it's really far away. So even with the Hubble Space Telescope, this is about the best that we can do. And the upper left of each side, you'll see the raw images, and then the bigger images here are the processed images. So the images that we have of Pluto right now are really basic. We don't have much detail on them. But you can notice that there are some bright areas and darker areas. And so what we know about Pluto right now still rather limited. Now, to give you a sense of how big Pluto is, this is an artist's conception, the upper left corner of Pluto compared to the size of the Earth. Pluto has about 1/10 the diameter of the Earth, so it's a very small object, and is actually even smaller than our moon. This picture in the lower shows many of the different moons in the solar system, and there's Pluto in the lower right corner, and then you can see our moon, two objects over to the left. So Pluto's a very small object, and so even early on, people realized Pluto's not quite like the other planets. Now, another thing that's interesting about Pluto is it actually has 3 moons of its own. This is another Hubble picture, and so Pluto is the bright object to the center, and just blown to the right of it is its partner moon, which is called Charon. And then there are in 2005, 2 more smaller moons were discovered called Nix and Hydra. So Pluto may be smaller than the Earth, but at least does get to brag that it has 3 moons, but we only have 1. Of course, our moon is bigger than Pluto, so I'd rather have our moon than Pluto, personally. So, as I mentioned earlier, even in the early days, people realized that Pluto was, well, not like the other planets, and there was something about it that made it, several things that made it stand out. Now, if you look at the solar system, you have the sun at the center, and then you have the 4 planets in the inner solar system, the 4 planets in the outer solar system, and then there was Pluto that was just sitting out here. And one thing I'll mention is this artist schematic is way out of scale. This is not the scale at all. So even early on, people realized Pluto kind of just doesn't fit in with the rest of them. So if you look at the terrestrial planets, the 4 inner planets of Mercury, Venus, the Earth, and Mars, they're all very similar to each other. They have dense cores made of rock and iron, and they have very few moons. Mercury and Venus have no moons at all. We have our moon, and then Mars has 2 small moons, which are actually captured asteroids. And another thing is the terrestrial planets, at least compared to the Jovian planets, are very small. So the terrestrial planets are all quite similar to each other, and the Jovian planets, which are the gas giants of Jupiter, Saturn, Uranus, and Neptune, were all very similar to each other as well. They're much bigger and much more massive than the terrestrial planets. And a big difference is they're made primarily of gas, whereas the planets in the inner solar system are made mostly of rock and metal. And a big difference is the Jovian planets have many moons, and so a big difference compared to the Earth and the other terrestrial planets, and they also all have rings. So just to give you a size comparison, this is how big Jupiter is compared to the Earth. And then just to put Pluto in perspective, that little period there, that little dot, that's Pluto for scale. So Pluto is teeny tiny, not only compared to the Earth, but especially compared to Jupiter and the other gas giants. So people knew that it wasn't like the other planets. So how is Pluto different? Well, as I mentioned, it's tiny. It's only about 1/4% of the mass of the Earth, and as I said earlier, 1/10 of the diameter. And another big difference is that Pluto is not made of rock or gas, but as I said earlier, it's made of ice. And another thing that's different about Pluto is that the orbit that it travels in is different than the other planets. And so this diagram shows the solar system as seen from above. Now, the orbits of the inner planets, the terrestrial planets, are so close to the sun, the red dot in the center there, we can't see them. But you can see that the orbits of the gas giant planets, Jupiter, Saturn, Uranus, and Neptune, are almost perfectly circular. Whereas Neptune kind of has this elliptical or oval shape to it. Sometimes it's closer to the sun, and sometimes it's further away. Now, if you tip the orbits of the planets on its side, you can see that all of the gas giants and the terrestrial planets all pretty much orbit around in the same plane, and this is called the ecliptic, whereas Pluto is doing this thing at an angle. And so Pluto is just kind of doing its own thing out there. So to understand why Pluto is different than the planets, you need to know a little bit about what's in the solar system and how it came to be. So of course, the sun is the most important thing in the solar system, and then you have the planets, the terrestrial and Jovian planets, and then you also have moons. And moons are a good example of something that are defined based upon their situation. If you orbit the sun, you have the opportunity to be a planet, but if you orbit a planet, then you're a moon. And as I showed you that slide earlier, some of the moons are actually bigger than some of the planets. Then we also have asteroids, and then we have another class of objects that have the unfortunate name of trans-Neptunian objects, or TNOs, and as the name implies, these are objects that are beyond Neptune. And one of the things that's kind of funny about astronomy is the names we choose for objects sometimes reveal our ignorance about it. All we know is they're beyond Neptune. That's all we can tell you right now. We'll get back to you and tell you more later. Now, this includes a bunch of different kinds of objects. You've heard of comets before. And it also includes objects that are called Kuiper Belt objects, or KBOs. And the difference between these two classes of objects is they're both kinds of chunks of ice, but comets will sometimes come in close to the sun and form tails, whereas Kuiper Belt objects always stay far away from the sun. They always stay outside of the orbit of Neptune. So to understand where all this stuff came from and how they're related to each other and how they're different, you need to know a little bit about how the solar system formed. And so this is an animation of how that process worked. About 4.5 billion years ago, a giant cloud of gas started to collapse. And inside that cloud of gas, the gas collapsed down into a disk or a pancake that was rotating. Now, most of the gas moved towards the center, and most of that gas became part of what's now our sun. But out in the disk, where all this material started swirling around, some of the material started to clump up together and form into planets. Now, what happened eventually is once the sun became hot enough, it started to emit enough light and energy to push away all the gas that was left over. And so whatever had not yet clumped up into planets, a lot of that stuff got blown away. I'm going to show that again just one more time so you can see it again. So again, we start off with this big cloud of gas, which is slowly rotating. And as it collapses, it starts to rotate faster and faster, just like a figure skater who starts to spin faster as he or she pulls her arms in. And then what would happen is most of the gas would move to the center into what would become the sun. And as this gas moved in, it would get hotter and hotter. And then in the outer parts of the disk, material would start to clump together. And the important thing is that material had to clump together into planets before the sun became so hot and turned into a star. And then what you had left over, once all the gas got blown out away from the sun, is what's left over. And so that's where your planets come from. I'll just mention those lines there are just the circles that represent the orbits of the planets. They're not actually there. But you knew that. Okay. Now, this is something that, of course, we couldn't see in our solar system because, well, we weren't around yet. But when we look at other places in our galaxy where stars are forming, we can actually see this going on. So if you go out on a clear winter night, you can see the constellation of Orion, which just kind of moves along the horizon around here. And there's the 3 stars in the belt at the center, and below there is a clump of gas called the Orion Nebula. And it's actually bright enough that you can see with your naked eye. It looks like it's a star, but it's actually a cloud of gas. Now, if you zoom in with a telescope, in case here we're zooming in with the Hubble Space Telescope, you can see that there's a bunch of stars inside this cloud of gas, and the light from those stars is illuminating the gas. And that's why we can see it. Now, if we zoom in further, there's 4 particularly bright stars here called trapezium. If we zoom in there, you'll see these little blobs that are all surrounding these bright stars here. And you'll notice all the blobs kind of look like comets. They have tails pointing away from the bright stars. These are smaller stars where planets are being formed around them. And zooming in particular, what you'll see is these faint stars that have these disks of material around them. And so what we're seeing here is what our solar system looked like about 4.5 billion years ago. So this is how planets form, and this is what happened in our solar system as well. So sometimes science is kind of like a 4-year-old kid that every time you get an answer, they ask you with, why is that? And every time you come up with another answer to that, you get why again. So we have a pretty good idea of how the solar system formed, but now we still have a bunch of why questions. For example, why are there 4 terrestrial planets, and why are there 4 gas giants, and why are the two different from each other? Well, the reason why they're different has to do with what's called the frost line. As I mentioned, the further away you get from the sun, the colder it is, and there's basically a distance away from the sun where once you get that far away, you can have ice. If you're too close, then the ice will melt. And so in the early solar system, if you're close to the sun, you had all this rock and metal that's swirling around, and they're trying to stick to each other to form into bigger objects and form into planets. Well, if you've ever tried to stick rocks together, it doesn't work very well. Now, in the outer solar system, you had a bunch of ice, and that ice and rock would stick together each other really well. And anyone who's made a snowball knows exactly what that's like, especially if you get some rock in there. You can make a real big, nice, nasty snowball. So in the outer part of the solar system, you had all this ice, and ice sticks together really well. So in the outer solar system, all these ices were sticking together, and they built into big planets very quickly. Whereas in the inner solar system, the rock didn't stick together quite as well, and so the planets in the inner solar system are smaller. So that's the reason why the planets in the inner solar system are just made of rock, and they're much smaller. Now, the planets in the outer solar system, what happened is they formed out of rock and ice very quickly, and because they had so much mass, they could grab a bunch of the gas that was in the solar system at that time. And so that's how they accumulated all the gas they have, and that's why they're gas giants. So now if we look at this list of objects, we can understand why we have all these different classes of objects much better. The sun is basically a place where nearly all of the gas and other material moved into the center. And the sun has about 99% of the mass in the solar system. And Jupiter pretty much has nearly all the rest. The rest of the planets are much smaller in comparison. So nearly all the gas moved to the center. The terrestrial planets are the ones that were inside the frost line, and they're just made of rock and metal, and they're much smaller because the rock and metal couldn't stick together as well. And then you have the asteroids, which is the belt of material that's past the orbit of Mars. And this is the material that there just simply wasn't enough of it, and there wasn't enough time for it to all stick together to form into a planet. So the asteroid belt is basically the leftover rock from when the solar system formed. It just never got it together to form into a planet. And so the outer planets in the solar system are made of rock, ice, and gas. And then the trans-Neptunian objects basically represent the leftover ice. These are the chunks of ice in the very outermost part of the solar system that never were able to stick together to form into a planet, just like the asteroids were not able to stick together to form a terrestrial planet. Now, I didn't mention the moons here, and the moons are just simply objects that either formed with the planets and started orbiting around them, or sometimes they were debris that were just flying along and they got captured by the gravity of a planet and started to orbit around it. So moons are very complicated, and I'm not going to talk about them today. But the important thing here is just I want you to see the pattern. You have the terrestrial planets and the asteroids, and then you have the Jovian planets and what are called the trans-Neptunian objects. And so you have the planets and then the debris from the leftover debris from their make. So it's like if you're making a pizza and you've got a little bit of pizza dough left and some sausage and pepperoni, and it's just kind of there. You don't know what to do with it. Well, in the case of the solar system, it just kind of stayed out there and kept going around. So this is all stuff that we've known for a long time. And so a good question that people ask me is, well, why is the International Astronomical Union dealing with this now? Why in 2006 are they dealing with this and not in 2003? Well, a lot of it has to do with just simple inertia. We wanted to make sure that we didn't change things until we were sure why we were changing things. And another big part of it is whenever someone said, well, maybe we shouldn't call Pluto a planet, a lot of people got upset, and we didn't want to upset people. And so we kind of started coming up with different excuses for why we should continue to call Pluto a planet. And what was happening, especially in the start of the early 90s, people started discovering more and more of these chunks of ice in the outer solar system, these trans-Neptunian objects. And people were asking, well, if we're going to call Pluto a planet, then why not this guy over here? And we'd come up with excuses and say, well, because it's smaller than Pluto. Yeah, that's it. And so we're going to just only have Pluto as the planet. Well, what happened in 2006 is an object which is now called Eris, which is the goddess of discord, which is a perfect name for this object, was discovered. And this object was found to be larger than Pluto. And so basically turned into the situation of, well, if we're going to keep continue to call Pluto a planet, then we have to call Eris a planet as well. And if we're going to include Eris, then we have to include all these other objects like Quora and Sedna and all these other objects we discovered. And so it became clear that unless we wanted to have our kids learning the names of several hundred planets, that we needed to start to distinguish between these different objects. Now this is a diagram showing the orbit of Eris, and you can see that Eris is even further away from the sun than Pluto. It's about twice as far away, so it's 10 light hours away. And you can see it has an even crazier orbit. It's going in this wacky orbit that takes it up and below. So it's clear that Eris is not like the other planets, just like Pluto isn't. So in 2006, the International Astronomical Union, we knew going into the meeting we were going to be faced with the issue of, for once and for all, defining what is a planet and what does that mean. Well, finally, after 2 weeks of debating, this is what we came up with. The first thing is we only talked about objects that are in orbit around the sun. So if you're in orbit around a planet, you couldn't be a planet. And if you orbit around another star, that excluded you as well. And one of the things that we're going to have to deal with in the future is how do we start to classify objects that we see orbiting around other stars? The second issue was, does it have enough mass for a self-gravity to pull it into the shape of a sphere? And the reason why this is important is asteroids are examples of objects that are too small and they don't have enough self-gravity to squeeze themselves into a sphere shape, and they just kind of look like these potatoes. And so you had to look spherical to be considered a planet. And then finally, you had to have, quote unquote, cleared the neighborhood around you. And what this means is that early on, when the planets formed, they gained so much mass that if any other object passed by it, that object either ran into the planet and stuck to it, or the gravity of the planet flung it out of the solar system. And so when you look at the material around in the inner solar system, like around Mercury, Venus, and Earth, and Mars, there's very few asteroids. And if you were to take all of the asteroids that are in the same orbit as the Earth, or close to the same orbit of the Earth, the total mass in those asteroids is less than 1/millionth the mass of the Earth. So the Earth is obviously the most dominant object. So if you were in an advanced alien civilization and you came to our solar system and you knew nothing about our planets, you could look at the Earth and say, yeah, that's the most important thing in this area right here, because there's nothing else around it that's nearly as big. And that's true for all of the other planets. But it's not true for Pluto. Pluto is only one of hundreds of objects out in the orbits beyond Neptune. And if you were looking at all the different objects, you wouldn't notice Pluto as being particularly interesting. There's plenty of other objects like it. So so to be considered a planet, you had to have done these three things. And Pluto, unfortunately, did not qualify for the third category. So we defined a second category, which is called a dwarf planet. And a dwarf planet is basically something that meets the first two criteria, but not the third. And so there are several examples of this. In the asteroid belt, in the trans-Neptunian objects, there's Pluto, there's Eris, there's Sedna, Quoar, and a few others. And then in the asteroid belt, there's other objects, larger asteroids named Ceres, that are now classified as being dwarf planets. Now, anything that that met the first criteria, that is, it's orbiting around the sun, but not the other two, was called a small solar system body. And as I mentioned before, if it's not orbiting the sun but is orbiting a planet, then it's called a moon. And as I mentioned earlier, despite the similarity in names, dwarf planets are not technically considered planets. And that's something I did not vote in favor for, but I was overruled. So this illustration here basically shows, as of today, basically, where all the different objects in the solar system are. Now, it shows the blue dots there for the planets in the outer solar system. It doesn't show the planets for the inner solar system. And then the pink dots there are asteroids that are called Trojan asteroids that follow and lead and follow in the orbit of Jupiter. And then the yellow dots and the green dots are what are called trans-Neptunian objects. And so you can see that there are literally hundreds, if not thousands, of these trans-Neptunian objects. And again, these are only the objects that we know about right now. And nearly all of these have been discovered in the last 10 years. And so you can just imagine that over the next 10 or 20 years, we're going to have thousands of these objects discovered. We're going to know about more and more. And so Pluto is basically one of those green dots. And it's very clear that Pluto belongs more with the green dots than it does with the blue dots, not to get too technical on you there. So here's an image of Pluto and some of the other trans-Neptunian objects that meet or nearly meet the classification of a dwarf planet. You can see Pluto there. Eris, which is the larger one of it, is to the left. And here are some other objects that have gotten various names. Now, we're going to be discovering so many of these things. People are going to stop actually trying to give it proper names, and we're just going to use really awful names like 2005, FY9, and things like that. For those school kids in the audience here, just try to imagine memorizing several hundred of those names for your next test. You'll be thankful we didn't make you do that. Now, as an example, sort of an analogy that I like to use with people, is one thing to keep in mind is that all we're doing here is just defining words, and those words are useful for helping us understand something about the object. So when I say that's a planet, I've told you something about it. It orbits the sun, It's big enough to pull itself into a sphere, and it's the dominant object in its region. Now, if I say something is a moon, then you know it's something that's orbiting a planet. Now, I haven't told you anything else about it. You don't know if it's made of rock or ice or what else it's doing, but you do know that at least that piece of information. So the analogy I like to use is, what is a couch? Well, if you're trying to explain a couch to someone, you say, well, it's something you want to sit on when you're watching TV or for long periods of time. Usually has fluffy cushions. That's a criteria for a good couch. And the most important criteria is that it can be slept upon comfortably. Now, in comparison, what is a love seat? Well, a love seat is an object that meets the first two criteria. It's fun to sit on when you're watching TV. Has fluffy cushions. But if you've ever tried to sleep on a love seat, you know it's not very comfortable. It's just too short, especially for me. So this is a way that you could define the difference between a couch and a love seat. Now, that piece of furniture up there is still the same piece of furniture, and whether or not I call it a couch or a love seat, it hasn't changed any. It's just that I've defined my terms. And in a similar analogy, you'd be say, like, what is the difference between a dog and a cat? Because someone who doesn't know the differences between dogs and cats, you say, well, they both have 4 legs, they both have tails, but one goes woof and the other goes meow. And that's the criteria you could use to distinguish them. Now imagine you have a friend who doesn't know what a cat is, and they see it as like, oh, that's a dog. It's like, well, okay, now we know it's not. So another question people ask me is, now that we've called it a dwarf planet, haven't we somehow slighted Pluto? Does this mean we don't care about it anymore? And one of my jokes is I say that there was an additional measure where we voted whether or not we should actually destroy Pluto, whether or not we should blow it up, and that didn't pass, so we're not going to do that. All we've done is change nomenclature here, and that is just a way to try to differentiate Pluto from the planets. And so, does this mean we don't care about Pluto anymore? And the answer is no. And to show our love for Pluto, NASA built a $650 million spacecraft that's on its way to Pluto right now, and it's actually going on the way to, after it studies Pluto, it's going to try to pass by 2 and possibly 3 more trans-Neptunian objects. Now, New Horizons was launched in January 2006. It passed by Jupiter in 2007 and released just some amazing images of Jupiter. You should go look for them online. But it's not going to get to Pluto until 2015. So for any school kids in the audience here, if you want to do a book report or report on Pluto featuring pictures from New Horizons, you'll probably have already graduated and gone on by then. So don't try to do that. So again, that's because Pluto is so far away. It just takes a really long time to get there. So again, notice it only took about 1.5 years for New Horizons to go from the Earth to Jupiter, but it's going to take, if I do the math right, 8 more years to get out to Pluto. So it's got a long ways to go. And New Horizons actually has the speed record. It's going faster than anything we've ever launched before. So here's a picture of the launch of the New Horizons spacecraft. And this is an artist's conception of what it looks like. Here is another illustration. And this just shows some of the different instruments on it. It has a whole bunch of different instruments that it's going to use to study Pluto. The big dish on top is actually used for 2 things. One is it's used to send radio signals through Pluto's atmosphere to see what it's made of. And it'll also be used to send the signals back to Earth, to send all the data. And then there's a bunch of different cameras and other instruments on here that are going to be used to study Pluto. Now this kind of mission was called a flyby mission, and what it means is that we're just going to fly by on Pluto and it's just going to keep on going. It's moving so fast that the spacecraft doesn't have enough fuel to slow it down so that it can orbit Pluto. And so it's sort of like when you were a kid and my parents were like this, like we were trying to get somewhere and we didn't have time, so it's like, well, there's Mount Rushmore, and you just see it as you're driving by and you take pictures as you drove by it on your way to somewhere else. So we're not going to have very long there. It's only going to be a few weeks where you're going to collect data on Pluto, but then we'll go see other objects. So here's just more illustrations describing where it's going to go. And so one of the things I think is very interesting about this is that now that it's past Jupiter for the next 8 years, every so often they're going to turn on the spacecraft and make sure everything's working okay. They actually just took the first picture of Pluto with the camera that's going to be used to guide the spacecraft to Pluto. And so they found it. But for the next 8 years, it's not going to do a whole heck of a lot. And then finally, it's going to get there in 2015. And then with NASA approving funding, the spacecraft will continue on and look at some other objects. So the things I'd like for you to leave today with, first off, is that The reason why we changed the classification is because science is a dynamic process. It's the process through which we learn things. And as we learn things, we want the information to get out to people, and we want them to understand what they mean. Now, I know what Pluto is, but I want everyone to know what Pluto is, and we want to make the distinction between Pluto and the other planets, because Pluto is a very different object than Jupiter or Saturn or any of the planets. And so the reason why we changed the nomenclature is because as we learn more about Pluto and the other objects, we want our terminology to reflect that. Another thing that's very important to note, and I think this is a bit of a problem that came out of all the attention Pluto got, is that all we did was we vote on nomenclature. What word are we going to use to describe Pluto? So astronomers and scientists in general vote on terminology, perhaps, but they don't vote on the science. So it's not like we have a meeting where we say, okay, if you like theory A, raise your hand. If you like theory B, raise your hand. Okay, theory A has it. You know, that's the right theory that explains everything. So if you like Newton, raise your hand. If you like Einstein, okay, Einstein wins, and so now we're going to go with Einstein. That's not how it works. Science was a process of experimentation, and that's how we learn what objects are and what things do. All we did here is vote on what we wanted to call Pluto. And finally, words are just words. We still love Pluto. It's still an incredibly interesting object to us. And one of the things that's ironic about this whole process is the more we discovered objects like Pluto, the more interesting Pluto became to us, because we realized Pluto isn't some strange oddball out in space. It has a whole family. There's thousands of Plutos out there. And so that was the motivation to send New Horizons out there to explore and learn what these objects are. If Pluto were the only one, people would probably say, oh, it's just some oddball weirdo. We don't care about it. But the thing that makes Pluto so exciting is it was the first object of its kind discovered. And now we know that there's thousands of them. And so one of the measures that was proposed at the IAU was to name this whole class of objects, the trans-Neptunian objects, to call them Plutonoids. And that's something I voted in favor of, but it narrowly lost. 183 people voted in favor of it, and 186 people voted against it, which was even closer than the 2000 election, and I thought we should have a recount, but they didn't do it. So in 2009, when we meet in Rio de Janeiro, one cool thing about astronomy is we get to go to cool places. We're going to bring this issue up again. And so one of my hopes is that we'll honor and recognize the importance that Pluto has played in the history of astronomy by naming all of these objects in honor of Pluto. And that's a tradition that goes way back in astronomy. There's many classes of objects that are named after the first one discovered. And I think that's an honor that hopefully Pluto will have as well. Okay, so that's it. And if you have questions, I'm more than happy to entertain them. The reason why New Horizons is put into hibernation, there's a couple reasons, but the primary reason is because NASA has many different spacecraft in the solar system right now that are exploring many different planets. So there's a mission called Cassini in orbit around Saturn right now. There's several space probes in orbit around Mars. In fact, Mars has better satellite television than Earth does right now because there's so many spacecraft in orbit around it. And NASA has to use what's called the Deep Space Network to communicate with all these spacecraft and pull the data down off of it. And so many spacecraft are just kind of left to sit out there for a while, and then the spacecraft is programmed to send signals to the Earth every now and then just to let it know everything's happening, everything's fine. So since it's really doing nothing until it gets there, the Deep Space Network will be very busy with other things.
Couldn't you just build a spacecraft like it and then add a rocket to it with a camera and just make it go around Pluto?
The short answer is yes, we could, and talk to your congressman about doing that, because we'd love to do that. The reason why that's not being done is because it takes a lot of fuel to speed up the spacecraft fast enough that it gets there within a reasonable amount of time. And then it takes a lot of fuel to slow it down once you get there. And the more fuel you have, the heavier spacecraft it is and the more expensive it is. And so this is the best we can do right now. Hopefully next time.
I have a question back here.
Okay, yes? I can't see you, but I'll hear you.
Is it a possibility at all that Neptune and Pluto could one day collide, or is that a pretty slim chance?
No, there's no chance at all that they will. The Pluto the orbits of Neptune and Pluto are in what's called a 2/3 resonance, which means that every 3 times Neptune completes an orbit, Pluto completes 2. And this means that they're always away from each other. And another important factor is that Neptune's orbit is like this, and Pluto's orbit is at an angle. And so every time Pluto's orbit crosses Neptune's orbit, Neptune's on the opposite side of the solar system. So the two will never collide.
Were there any other questions?
Hand right here.
You said that the large planets in the outer solar system are there because they're outside the frost line. Most of the extrasolar planet-like objects have been huge gas giants, they've said, and they're all very close to the stars that they orbit.
That's right. When we look for planets right now around other stars, mostly what we're finding, as you say, are gas giant planets, planets the size of Jupiter or even larger, that are actually very close. And the reason why this is those are the kinds of planets we can see very well right now with the techniques that we use. The prevailing thought right now is those planets originally formed further away from the star outside the frost line, and while there was still gas in the disk there, it provided enough drag to cause the planet to spiral in to while it was closer to the star. So why that didn't happen with Jupiter and the other gas giant planets, we don't know. And that's one of the things that's very interesting is that all we have so far is our solar system to study. And we have no idea whether or not our solar system is very typical or if it's very unusual. But we do see many of those planets. And there's an exciting new mission called Kepler that's going to launch next year, which is going to be able to discover planets like the Earth around other stars. And so that will be when we'll really start to have enough information about how unusual is it to have Earth-like planets around other stars. Okay, if you want to go ahead.
Just to play devil's advocate, one of the third criteria you put up there about in order to be a planet, it has to clean out its local neighborhood or something to that was the terms you used. That it doesn't sound very scientific, or it seems rather subjective in terms of what you mean by cleaning out the neighborhood around its orbit, because maybe if you look at some of those trans-Newtonian objects, the distances between those objects is still greater than the distance between terrestrial planets. And so you could say the Earth didn't do a very good job about cleaning out its local environment because there's still Venus on one side and Mars on another. So was there an actual value that was given for distances in terms of what constitutes a neighborhood?
No, a value wasn't given, and that's been one of the many complaints about the definition is that it's not clear what it means to clean out its neighborhood. I think a more clear definition would be to say what fraction of the mass in orbit at that distance from the sun, what fraction of it is in the planet and what fraction is in other objects. So as I mentioned before, in the case of the Earth, the matter inside the Earth is over 1 million times the sum of all the other mass in that orbit. Whereas in the case, if you look at Pluto, it's only less than 1% of the mass, all the mass orbiting around there. So I think you can make a very clear distinction there. But it is poorly worded, and that's something that will be addressed in 2009. Now, one of the there's several different problems with it. For example, you can't have criteria 2 without having criteria 3. If the object is big enough to pull itself into a sphere, it will also be big enough to clear its neighborhood. So that's actually redundant. But the reason why that was put in there was mostly politics, because you have the planetary geologists who care what the object is, and then you have the solar system dynamicists, which care what the object is doing. And so criteria number 2 has to do with its physical size, and criteria number 3 has to do with whether or not it's actually scattering other objects. And if it can do 2, it can do 3 as well. So it's redundant.
Travis, we have a question here.
Yes.
It has to do with the difference between the Jovian and the terrestrial planets.
Yes.
The Jovian are bigger, but if they were compressed down so that the gases were not quite as expanded but were more solid, would they still be bigger than the terrestrial planets?
Oh, yes, they would be. The mass of Jupiter is about 100 times the mass of the Earth. And in fact, if you were to strip all of the gas off of Jupiter, so all you had left was the rock and the core, it would still be about 10 times bigger. Now, one of the things that's interesting is that if you actually add more gas to Jupiter, it will actually start to get smaller because the added mass will increase the strength of gravity and it will cause the planet to squeeze even more. And so it's an irony of the gas giants. The more mass you add, the smaller they become. There. Okay, yes.
So how come you don't call Pluto a planet anymore?
Didn't I just go over that? Like, well, I think for a long time, many people, including myself, have resisted the change because we knew a lot of people would be upset. And I think the thing that finally swayed me was that, you know, science in general, but scientists in particular, have an obligation to the public to be honest and truthful about what it is that we've learned. And I think people would be even more annoyed with us or upset if we said, well, really all along we knew that Pluto wasn't really a planet, but we didn't want to upset you guys. I think that violates the trust that we have with people. Our job is to learn about how things work and to properly convey that to people. The reality is people are upset about Pluto because of Pluto the dog, not because of Pluto the planet. I've never seen so much love and anguish over a giant chunk of ice. I mean, it would be like if you kicked your mud flap and a chunk fell off and 100 people just ran up and screamed, why, why? You know, that's kind of how I see it, you know. You know, the attention is great because, as they say, you know, any attention is good attention. And I think it brings a lot of insight into the process of how scientists work. But in the end, it's just a word, whether we call it a planet or a love seat or whatever. Pluto the love seat, I like that. That's good. It's just a word. It's the same object no matter what we call it. Yes?
My teacher said that she said that Pluto could have been a moon drifted out from a different planet. Could that be?
There's no evidence that Pluto was once a moon and then left. And the reason why that is actually quite clear that it was not once a moon. Originally, people thought it might have been a moon of Neptune that somehow got stripped off. But if it were once a moon of Neptune, then every so often Pluto would pass by Neptune. As I mentioned earlier, Pluto and Neptune stay as far away from each other as they can. And so there's no evidence at all that Pluto was once associated with Neptune or any of the other planets. Now, the converse does seem to be true. For example, the largest moon of Neptune is an object called Triton, and that's almost certainly an object that was originally a trans-Neptunian object that was captured by Neptune and is now in orbit around it. So that object, Triton, definitely became a moon, whereas it's clear that Pluto never was.
One over here.
Yes, sir. Yes. Or, no,
I was just wondering, is there any particular reason that Pluto has an elliptical orbit, or is it just you know, a random thing?
The reason why it has elliptical orbit is because it has passed close enough to one or more of the gas giant planets to disturb its orbit. Now, the orbit of Pluto is just slightly at an angle, and is still considered what's called a Kuiper belt object. And Kuiper belt objects are objects that have not been significantly affected by the gas giant planets. But Eris is another class of object called a scattered disk object, and what that is it's an object that certainly in the past did pass close by one of the gas giant planets and then got thrown out into this strange orbit. So where all the planets are going like this, it's going around like this. And so that's almost certainly what happened to it.
Yeah, this is. I wanted to ask about the other deep space sort of missions, because whatever happened to the Voyagers, I was struck by how quickly this last mission is making it out of out into the solar system.
The Voyager missions, believe it or not, are still running, even though they were launched back in 1976. For those of you who can think that far back, do you remember what computers were like in 1976? Okay, yeah, some of you are nodding your head, and some of you are going, I have no idea what you're talking about. It's amazing. When the Voyager probes were made, they were hoping they'd make it to Jupiter before they conked out. And they made it to Jupiter, and then they continued on to Saturn, and then Uranus and Neptune, and they're still going. It's amazing. Both the Voyager probes are still operational. Now, the Voyager probes are running across two problems. One is the further away they get, the fainter and fainter the radio signals get, and so there will eventually come a point where we can just no longer hear them, when we can't receive the signals from them. The other part of the problem is they're powered with a nuclear generator that's slowly losing energy, and so the signal, not only are they further away, but the signal is getting weaker. But they're hoping that they'll make it so far out until they reach what's called the heliopause, which is basically the point where you leave the influence of the sun and you're just out in deep space far away from it. And they hope that they make it that far. But amazingly, they're still out there and they're still going. It's American ingenuity for you. Okay.
You showed a fascinating animation of the evolution of the solar system, which I guess is largely an artist's concept in some ways, but I'm sure that there has been some success with computer modeling of the evolution of the solar system to its current state. To what extent are we actually able to model this in computers and make it look like it actually is?
Well, you're right. What I showed is just simply an artist's conception, and the whole idea there is just kind of shrink down the key elements into a very brief period. But all of the things that I've described have been intensely modeled with computer modeling. One of the biggest issues in modeling these sorts of systems is the stability of the orbits. As the planets interact with each other, they can have a tendency to get kicked out very easily. And so computer models are not quite yet at the point of being able to tell us whether or not getting kicked out of the solar system is something that's easily avoided or very hard to avoid. So for example, the conventional wisdom has said that we're lucky that Jupiter is here, because Jupiter, being so massive, got rid of a lot of the junk that could have hit the Earth and caused a lot of trouble. And some people actually say we would have been better off if Jupiter weren't here. Because more things would have hit the Earth, and that would have caused evolution to go faster on the Earth. And so it's still something that's very poorly understood. But all the stuff I described is based upon theoretical modeling and observations of other protoplanetary systems.
Is there anything else? All right, thank you.
Thank you all for coming.